CLion, a cross-platform IDE for C and C++. Download now.
Good, whatever part of the day you are in. Glad you could join me. Hope there's many of you. We'll find out later. Today I'm going to talk about type traits and compiler intrinsics and static reflection and how they may soon enough come together and open up new possibilities. The general agenda for today, I will start with a quick introduction to type traits as they are today. There are two main implementation strategies, template-based and via compiler internals, also known as built-ins. Then a quick intro to static reflection, upcoming in C++26. And then what the potential might be for interaction between reflection and type traits. A quick introduction of myself. I'm Andrei Zissu. I've been developing in C++ in Israel for over 2 decades. Back in the 80s, I came in from Romania when I was still a kid. Romania was still a communist country. I worked in several industries, in most of them as a C++ developer, including in embedded, and now it's my second place in a defensive cyber startup. And I've also been a member of the standards committee for the past 3 years. At my current job, I work at Morphisec. We do something called automatic moving target defense, which basically takes the attack surface malicious attacker would have to work with and scrambles it so that even if they get in, they can't find whatever they might be looking for, and they also get caught in the process. That's very interesting stuff. I've mentioned both the standards committee and my current employer, neither of whose views are expressed in this talk. So this is the disclaimer. You will be hearing my personal views here. Hopefully they will also be yours in 1 hour from now. Let's start with the introduction to type traits. So type traits nowadays are an important kind of they are a way prior to reflection being available. They are the way we have today of doing a kind of compile time functions, which can return either a Boolean result or a type whenever we do some type transformations. The second thing, returning types, is possible nowadays only this way. And returning a Boolean result has been possible since C++11 also via constructor functions. So this is generally how type trace would be used. To anyone who is not familiar, in this slide you can see the new way with if const expr, which allows you to put such expression in one function, and on compile time only the branch that checks out is actually compiled into actual code, which makes for nicer code in a single visually. Visually, it's a single function. It would compile into several actual functions. The old way would involve using enable if, which behind the scenes works on Spine, which we'll also be discussing shortly. In this case, the function is broken up into 2 parts. We are expecting at least one of them to match, and then that one would be found by overall resolution and would be compiled to the actual code. If nothing matches, we get a hard error. As you can see here, this is the long form that was at first available. When we have to do those dots with and to add either a dot value or dot type, which is a bit cumbersome, which is what the new helpers were introduced for. We have two kinds of helpers. You can see here the underline V, which returns a value, underline T returns a type. It's short for those dot value and dot type. And this is the way nowadays we'd be writing this kind of code and using type traits. So in this case, we have the first print, which is only invoked if T is an integral type, and the second one would be invoked for any floating point type. The type trait will do the checking over the of the actual type being passed and see if and return the Boolean result. Just a quick selection of some type traits. There are obviously much more than those. These are the categories as categorized at cppreference.com. Not much to say about those. As you can see, and they check a certain trait of that specific type, if it's a function, a pointer, if it's an L-value reference, and so on. Those are are composed of several traits. A scalar could be several possibilities. Could be an integer, could be an enum, could be a floating point. So in turns, this kind of composite trait needs to invoke several other ones and see if either of them matches, and then it would return true type. Also some type properties, which are quite straightforward. And there are lots and lots of supported operations which can be checked via type traits. You can check if a type is trivially constructible, if it's constructible from some other type, if it's copy constructible, if it's assignable, and again, so on and so on. All the types that we've seen so far are unary types. They appertain to one type. There are also type traits which are categorized as type relationships. Those are applied to two types and to establish a relationship between them, ascertain whether such a relationship exists. And now to type transformations, those, again, it's just a small selection. Those are basically functions, you could call them meta functions, which take a type and return a new type with a certain transformation applied to it. We'll also see this in more detail later. I encourage you to read more about this stuff on CPP reference. It's always the best site for things C++. A few general notes. I will be referring to intrinsics built in as magic intermittently, although they don't really have exactly the same meaning. In general, it refers to some internal access to something in the compiler, in the EST, the abstract syntax tree, which the compiler uses to represent the code once parsed. And this kind of intrinsics gives such direct access. There will be obviously a main part of this talk. I will be talking about type traits. There are also concepts, many of which are built on top of type traits. I won't go into details about those. I'm just mentioning their existence. I will be referring in detail to the three main vendors of both compilers and libraries. Those compilers and libraries are nowadays strongly attached to one another, with some exceptions. And this will be part of the latter part of my talk. The three main ones are Clang, which comes with libcx6 or libcpp. GCC comes with libstd, and Visual Studio with its own open source library, unlike the Visual Studio compiler, which is the only one here which is not open source. You are totally forgiven if you confuse libcx6 and the libstd, which comes with which compiler. I'm never able to remember that. Okay, so let's discuss the main type trait implementation strategies. So there are type traits may be implemented via template machinery or via intrinsics, and very often via a combination of both of them. We'll start with template-based implementations. There are several basic building blocks, the main ones. There are many others, but I think those were worth covering in a little bit of detail. So there is integral constant. Integral constant allows you to obtain a value at compile time, to kind of move it to the compile time world in a way which makes it kind of wrapped in a type which can be reasoned about by compile time tools. So the way this is done is that you have a template over the type of that value, and then the value is itself as a non-type template parameter. And then it's reflected outwards via the value data member. And we have the true type and false type helpers, which are partial template specializations over the bool instantiation of integral constant and either true or false values thereof. And there is bool constant, which aids us in working with this kind of integral constant. That would be the type of either true type or false type. Now to enable if. Enable if expects a Boolean template parameter, non-type template parameter, which can be either true or false. In the false case, which is presented here as a primary template, it translates to an empty struct. In the true case, the struct also has the type member, which reflects the second parameter. So this kind of allows you to have a sort of if at compile time. And this preceded if const expr by some 2 decades, I suppose. It was the only way of doing such things. And it also has its own helper, type alias. Now, the technique for using this kind of stuff, the old way would have been with either successful or failed substitutions, which you might know as substitution failure is not an error, also known as sphenay. Which means that if the substitution into one of those instantiations results in an ill-formed expression, this does not ultimately result in a hard error, but rather that specific instantiation is taken off the overload set, does not participate in overload resolution. The other ones still do. If neither of them generates a match, then we get the hard error. Just to have a rehash of what all of this means, we've seen this slide before. So we would get here okay. So we have enable if t, the short form. It expects its Boolean non-type template parameter. Then we have is integral v, which performs its matching, seeing whether t is an integral. If it returns a true type, enable if t will in turn resolve to true type. Will resolve to the struct which has the type data member, making this this specialization well formed in this case. If not, then we proceed to the next one, and you get the general idea. As to the implementation of the helper variables, it's very straightforward, just a template variable, const expr. Now to a couple of main ways of implementing template-based type traits. The first one is via structs. You basically implement a struct which must have a which you derive from bool const or integral type. In practice, we derived it from either true type or false type. So the idea is that the default case is derived from false type. We have afterwards a set of we can call them matchers. All of them are derived from true type. So if any of them generates a match, we're gonna get something derived from true type, and we'll have that type data member. We can see a similar case here. And this can be viewed as a kind of logical programming, pattern matching, whatever you might like to call it. Remember that templates, when templates match their parameters, that's not like overload matching, in that the matching must be precise. There is no explicit conversion. That's something to bear in mind. Here is a bool constant in this case. Similar technique. Bool constant itself is a variable template, which brings us to the second technique, which is by implementing variables. So in this case, we implement the trait via implementing a template variable, which translates to either true or false. And we perform the matching inside the template parameter of this variable. And we can see in this case, coming from Visual Studio, they flipped the previous scenario. Previously, we had a struct and a variable, a template variable as a helper, and the logic was in the struct. Microsoft implemented the variable template as the main focus point of the logic, and the struct is implemented in terms of the variable. Both techniques work just fine. Now, let's proceed to type traits, which are implemented via compiler internals. And we'll see some code. So here's Clang, or rather the lib cpp, if I'm not getting it wrong this time. So we can see lots of the type trait implementations are accompanied by if-defs checking if a certain built-in is present, which I would presume to mean that once upon a time, the sole implementation was the one based on templates, and then they started adding built-ins. Also, they need to be compatible with, backwards compatible. But the built-ins are the preferred choice whenever they're available. Also, some of the if-defs, which we will see, provide support for other compilers, but they don't provide this kind of support to all compilers, and I presume they would be quite cumbersome to maintain going forward. Not all of them have this kind of differentiation. This kind, they always go for the built-in. If it's not available, you just won't get this type trait. Here too, it's straightforward, presumed the built-in is present. We're looking at GCC now. You can see all these implementations are really straightforward, trivial. There's nothing to see here, basically. In MSVC, similar story. Sorry, we're still in GCC here. Yeah, we're seeing again, it also makes this selection between whether it can use a built-in or it has to use templates. In MSVC, there are lots of type traits built on top of Intrinsics. But there are also many others which go a different path. And in particular, there are cases such as this one. MSVC in general has support for Clang. You can compile with Clang from within Visual Studio, which means they need to have the same library support too. So their library is compatible with being compiled with Clang, so they do this kind of if-defs. The interesting things is that they use the Clang built-in, but if you don't compile it with Clang, they go with the template-based implementation, which looks like this. And this is a simple case proven by the fact that I managed to cram it into a single screen. So I've taken the liberty to do some very unscientific charting using dot graphs, GraphViz. And I took some selection of type traits and tried to map their interdependencies in the three main compilers. Let's see, the first one. Intentionally, you are not supposed to see much here. The only thing to pay attention to is the blue thing here and the red thing. In any case where I reached a node where the rest of the implementation is template based, I marked that as template, which the root of all of those is this blue thing here. And everything that is a built-in, I marked it as if it has a dependency on something called built-in, that's the red thing. So this is in Visual Studio, you can see that about a third of this is on the left side, which means it's based on templates. All the other stuff is internals. That's most of it, although it's also more shallow. Now we get a little bit into more detail from left to right. This is the part implemented via templates mostly. As you can see, the lower row here, the lower part here, all of those are starting with underline. Those are actually built-ins. There would be an arrow going way past them to the right, all the way to the built-in. So most of what you see here is really based on template implementation or is a mixed implementation. And it's also quite tangled. There's lots of layers here. So it does indicate that those implementation would be quite complicated. Going more to the right, we are finishing the template-based part and going into intrinsic-based. We're done with Visual Studio. Now in Clang, the template-based part is very tiny in comparison. I mean, it ends just about here. And it's also more shallow. This is a focus on the entire template-based part, which is even less than you may think, because all of this part is actually intrinsics. Going to the right, we get only built-in based type traits. GCC is somewhere in between. It seems to have a history of having started with template based, but it's been drifting towards intrinsics faster than Visual Studio has, but it still uses more template-based type traits than Clang. So here's the template-based part. We have here intrinsics permeating basically up almost to the very top. So I think about half of this is actually either intrinsics or mixed type traits. And of course, all the rest is based on intrinsics. And doing a quick comparison of those three, we can see again MSVC, which has comparatively lots of type traits based on intrinsics and to a great height, lots of layers and quite tangled. We can see Clang, which is on the other extreme, and GCC middle ground. There are a few assumptions and caveats to how I produced this. In many cases, as I've shown you, there are both alternative implementations, both based on intrinsics and on templates. In such cases, I showcased only the intrinsic path, assuming that going forward, That's the way they will take, and the template path is only for legacy purposes. I only focus on standard type traits, not on vendor extensions, because that would kind of defeat the purpose. The details are sometimes simplified. In some cases, there are some intervening template layers which I'm not showing. I only covered about half the standard types, and of course, I probably have made some errors. Quick note on present cross-chain support. These are the two I've identified. The MFVC library has if-defs, which for supporting Clang. Same for libcpp, which is also able to support compiling with GCC. There may be others which I haven't noted. So the current implementations, as you've seen them, do have their drawbacks and limitations. The implemented this way via templates gets very complicated very fast. This would mean, I presume, the maintainers of those libraries may occasionally have quite a hard time. And as I'm sure all of you know, it's not fun figuring out what the compiler means when you misuse some template and need to figure out all those error messages. It should have become better with concepts. I believe it has only to some extent. Templates may also, the abundance of templates may also lead to slower compile times. And some of those, especially the composite traits, would require future maintenance. For example, is integral. If ever a new integral type is added to the language, then someone needs to remember to add it there too. Of course, also to the standard, but also the implementers. So there's more to implement there. And there are some cases, such as implicit lifetime, which is simply not implementable via templates. They can only be implemented nowadays via built-ins. And yes, that means currently you don't have a really portable way of implementing them. And talking about a portable way, it's time to talk about static reflection. So first of all, what do we mean by static? As we all know, we in the standards committee absolutely love the word static and always appreciate new ideas of new meanings for this word, because there are simply not enough of them. But for our purpose today, we only focus on the meaning of static as something happening as compile time. That's the meaning relevant to reflection. And that's why we're discussing static reflection. Other languages also have dynamic reflection. I would say static reflection, once it comes into C++, would be much more powerful than dynamic reflection in other languages. And same as C++ templates are more powerful than their dynamic generic alternatives. The current state of reflection, as of this moment, reflection is an approved part of C++26. It's been voted at plenary in Hagenberg 2 weeks ago. It's the value-based approach. Shortly, I will discuss the other approach. It's still, well, I made a small error. It's not yet voted in, but it's in wording phase, which means it's been approved by all the subgroups. Right now, the wording phase is being completed. It must be completed in Sophia, in June and then voted by plenary, and then it will be in C++26. The expectation is that this will indeed happen. It includes introspection, which means you can analyze the code and reason about it. It doesn't include injection, as in creating new code, except for the relatively simple cases of creating types, not actual logic, but types via either splicing or define aggregate. Splicing basically takes a reflection of some types and reifies it, moves it back to our normal world. And define aggregate takes a set of description of fields and synthesizes a aggregate struct, which can only contain public data members, basically. It's also likely as a separate paper, which has also been approved. It's likely to include expansion statements, also known as template 4, which will be extremely useful. It doesn't include AST modification, so you can't change something that's already part of the code that you've already compiled. But you can have kind of meta functions which purely return reflections as values, and then you can splice those into the AST, but you can change something that's already in the AST. When I said value-based, the value is something called meta.info, which is an opaque type. There's basically only this type and lots of meta functions which have been defined in the reflection paper P2996, which operate on this kind of values. And the motivation for doing it this way was mainly to be future compatible with any future changes in the type model of the language, and also so that reflection itself won't be a hindrance to such future changes. There are suggestions, including mine, of building typeful libraries around this. I hope this is something that can be done in the C++29 type frame. And were such classes to exist, they could have a conversion function to convert them back to meta-info and thus be easy to work with. Meta-info itself is somewhat reminiscent of the definition of null PTR, in that it's in terms of some decal type. So it basically, its definition is that it's the type of the reflection of the global namespace, but in fact it can reflect lots of things which are listed here. This is taken from the actual paper. There are a few things it can't at present reflect. First and foremost, expressions, which I very much hope we'll get in 29, but there's lots of other things, mainly types and values, which can be reflected. Some short examples from the paper. We can see here. So we are starting with an int. We reflected and create a reflection. R is now a reflection, a meta info. Of course, it can only be const expr. It only lives at compile time. And here we take the reflection and splice it back. So we get an int back. So it's same as int x equals 42. Here we do the same thing with a char. The type name part is similar to templates, as in it's compulsory in ambiguous contexts, is optional otherwise. Here we have a selection function which we provide with an offset, basically, and it returns a reflection of the member at that offset of struct S. So we can see here, as I mentioned before, this is basically a pure value-based function. It can't modify the AST, but it can return a reflection. This is only meaningful at compile time, so all of those functions will be const eval. Its logic is very simple. Of course, here we need to reflect. In order to return a reflection, we need to produce one. So this is what we're doing here. And at the call site, we splice it and we get the desired result. We get a hard error in the second case because we do not have an offset 5, which makes the call not a constant expression, and thus hard error. Another example here, which also shows us that this meta-info objects are nowadays, they can fully leverage all the latest addition in the const expert space. We can use them with containers, ranges, range algorithms, and we can build some very powerful constructs. So in this case, we have an array of type reflections, and we have a lambda, which we provide to the range transform, and it takes this array of size-offs basically, and it modifies their values to reflect the actual size-offs of each and every type. This is an enum to string example. Now the thing to note here, in this case, this member number, this is not part of actual generated code. This is a const eval function. In this case, we are actually producing a const expr function, which will be available at runtime. Arguably, I think this might actually be a mistake in the paper, because currently stud strings cannot be returned at compile time until we get non-transient memory allocations. But this is definitely something that will work at runtime. So what we can see here is that the expansion statement I mentioned before, and it looks like a loop, but it actually expands into a repetition of statements, and in this case, the loop is over a set of values returned by this meta function, but it could just as well be a set of types. So you can loop over a set of types treated at compile time as first-class citizens, and the statement inside the loop will be basically unrolled into a repetition of statements, one for each instance. So I hope you can see how this is something very powerful. In this case, it would translate into a set of checks, of ifs. And the first one that finds a match, of course, will return it. We have here another meta function provided by a reflection, which takes the enumerator and returns its string representation. So now a word about type-based reflection, which was the other reflection flavor which was discarded a few years ago. The idea was not to have opaque types, but to have an actual type hierarchy, template type hierarchy, representing basically the language model. It would have made it easier to work with, because you kind of need to get your bearings when you need to figure out for each meta info in each role which meta functions are applicable on it. But it did have a couple of main sticking points. It was expected to suffer from long compilation times, since compiling such an abundance of templates and instantiating them requires the compilers henceforth to keep them in memory. So the compiler would have had a large symbol table and a large footprint, and that would of course also affect its performance. And as I mentioned before, it might not have been future-proof and hindered the language development itself, or at least that was the concern. Now to the ultimate topic of reflection and type traits and my speculations about it. So looking at all those type traits and all those built-ins used to implement them, frankly, this was not my original intention when I started preparing this talk. But then I noticed, okay, we have reflection, for instance, coming very soon. What if we could use reflection instead of type traits? I've had some discussions about it. Not sure anyone has even discussed this before. This might be introduced either by, not sure if it would eventually be introduced by the standard itself, or just as a quality of implementation thing. I wrote a proof of concept, which you can access on Godbolt, using the Bloomberg implementation on top of Clang. And I had quite a nice time using Microsoft Copilot with its Think Deeper mode, which was just came into being early this month. And it's very helpful with generating code, but don't worry, you'll still have plenty of work to do afterwards. So I wouldn't be worried about my job at the moment. Culminating in, ultimately, I gave it the final correct code just for letting it learn, and it actually modified it and brought me back incorrect code. That was fun. So this is from my POC, which is basically everything there is very straightforward. It's a set of mappings from the type trait I used to implement to its matching reflection meta function. Here it's slightly different in this case. I decided to go this way to use the istem type as Copilot suggested. But it's still very simple. You just, well, you get the idea. The other case is the type modifications with the aid of template variables, again based on the reflection versions. You can see that in both cases, the template parameter is a type. Now, those types, which we've known for some 3 decades, they are a compile time entity. Now, reflection is also a compile time entity, but there are two kinds of entities. They, in the reflection world, it's kind of being in the internal world of the compiler where the AST also lives. And in that world, reflections are first class citizens, and you can do with them the same kind of things that you can do with variables in our normal world. So you constantly need to convert between those worlds. So in each of those cases, I have a template parameter. I need to reflect on it. And by the way, this has been nicknamed the unibrow operator. This is a reflection operator. Until recently, it was just a single one of those, but there were some concerns about it. So it's now unibrow. So I guess it would be good friends with the spaceship operator. You might raise a brow at that. So in all of those cases, we have this dance of reflecting on something, then doing whatever we need to do with it. And ultimately, in order to do something useful with it, we need to splice it all the way back. Now, to the big question, speculative question. And I must say, I haven't done any actual performance measurement, so you're gonna see a set of speculations. First of all, I think it's worth looking into. Might be possible, might be worth it, but it's definitely worth looking into. I would presume, given those, in some cases, very complex template-based implementations, which are both hard to maintain and also hard to compile and slow to compile. In some cases, reflection-based type traits might get perhaps a little bit slower, because in implementations that I show you, there's a thin layer, there's a thin template layer that you apply on top of the reflection, instead of just calling straight into the reflection itself. Basically, the meta header itself is implemented as a big set of such thin template wrappers, which call into some built-in. As you've seen, in all those cases where there is a matching reflection trait, the code would be trivial, and I think this is a vast majority, and I call this the low-hanging fruit. And another concern I have, if we don't do this, is that we'll wind up in a world where you have two ways of doing the same thing, of obtaining the same information. And that's not very good in itself, but one of them might be buggy, because they might have internally two different implementations. One of them might be buggy. There's an example of something from Clang. I think it's trivially copyable, which for some 7 years it's implemented in a way which can now no longer be modified, but it deviates from the standard. And now comes the big question: okay, what do you do about reflection? Do you proliferate the bug, or do you create divergence? There's two not very good choices. And I am a strong believer in implementing things in terms of one another. It's also a very DRI thing to do. So just to summarize, as we all know, type traits are a very important tool for generic programming. The single ways basically nowadays of implementing them are templates and compiler intrinsics. Implementing them via templates is hard for both the human and the compiler. But the good news are static reflection in C++26, which has taken the value-based flavor, meta info being that value. Unfortunately, it will initially not include code injection, which is something I very much hope to have in C++29. It includes lots of meta functions on top of meta info, which are very reflective as of the current type traits. Of course, there are also additional things in there, which would apparently make those type traits trivially implementable via reflection rather than either built-ins or templates or both today. Which begs a big question. Could we leverage all of this to have the standard library itself made portable? Nowadays, the standard library provides portability for user code, but could we have portable standard libraries and be able to mix and match them between different compilers at will? We have that to some extent today, but only because we have custom support for that in the forms of those if-defs. But one day, perhaps, I don't know, decade hence, we could have a compiler-specific meta header, perhaps a few other headers also that cannot be made generic, and have everything else be fully generic and portable and interchangeable. If this were to be feasible and to actually work, it would give us lots of freedom in exchanging those things. We might want to use a compiler from a specific vendor, a library from another one, because everyone has their own strengths and weaknesses. I remember the Visual Studio library not implementing the stud file system for several years post C++17. So I think that would be a great thing to have. Might not be straightforward or even possible, but if it would be great to have. And I think it can be done gradually. More and more parts of a standard library could be moved over to the generic part and ultimately wind up in this kind of situation. Again, this is my own very recent opinion, might be misguided, not even remotely a stated goal of the standards committee, but I think it would be an interesting discussion to have. Thank you for joining me today, and have great reflections and a great future.